All right, can you hear me?
We can always hear you. That's
all right. It's good. So, so I was determined to outdo Tillman. So I approached several of the students over beers and said, if you're willing to email Tillman and tell him that my lectures were better than his, I would purchase your beverage. I bought a lot of beers. And then they all promptly emailed Tillman saying that my lectures were better than his because Dan paid me in the form of beer to do this, which really defeats the point. So I won't be falling for this again. That's really the gist of the story. That's the punchline. All right, so I'm going to talk about dark matter with the indirect detection focus. By indirect detection, you could imagine I mean a lot of things, but historically it was a way of dividing scattering with ordinary matter, what we call direct detection, from other ways of detecting dark matter. So if you are talking about experiment like Xenon 1 ton or CDMS or any of these underground detectors, they're really looking for the dark matter particle to come in, hit something in your target material, and you detect that collision. That is not what I'm talking about today. I'll mention it in passing, but that's really not what it's going to be about. Instead, I'm going to be talking about particles, high energy, well, not necessarily, particles that are produced in, for example, the annihilations or decays of dark matter particles. That's what I mean by indirect detection. Depending on how fast these things go and whatever, I might talk about a few other ways of indirectly detecting dark matter, but I'm not exactly sure how much material I'll get through in these 5 lectures. So before I get started, I want to implore you to interrupt, ask questions, challenge me, tell me what you already know and I should move on from, and tell me what you don't already know that I need to explain better. All of that stuff will make the lectures better for you, and most importantly, they will make them more enjoyable for me, because I get bored really easily, and an hour and 15 minutes of my own voice will be terrible for me. So I don't want that. I want a dialogue, so I need an oath, I need a show of hands pledging to interrupt my lectures as often as possible. Yeah, there you go. Yeah, I like this guy's enthusiasm. So, but seriously, like the more you interrupt, the more you participate, I think the better it will be for everybody involved. Agreed? Right. That's contractually obligating. All right. So I want to start not actually with indirect detection, but for the motivation for indirect detection. And it will help us also get to some important benchmarks for dark matter indirect searches. And I want to do that by just positing or posing this following question of how the dark matter that we find in our universe was likely created. Okay, so there are lots of different generic pictures you can consider. So I could imagine the process that's generically known as thermal freeze-out. And we'll talk about this in some detail in the part of this lecture. But just for right now, I'll say it roughly means something like this. Here we have something like the co-moving number density of WIMPs, or I should say dark matter. I'm not necessarily talking about WIMPs yet. And the idea is that you have an equilibrium abundance. And at some point in time, these particles stop interacting in a way that depletes their abundance, and they become a flat co-moving number density. They stop disappearing from the universe. This is what I generically mean by thermal freeze-out. So you start with something in thermal equilibrium in the early universe. It evolves until it's no longer in thermal equilibrium. It has stopped evolving, and that stuff that's left over after the process is the dark matter. So that's what I mean by a thermal WIMP or a thermal freeze-out picture. So that covers a lot of ground, but what other scenarios could I consider to produce a dark matter in the early universe? SIMPs. Okay, tell me what you mean by that, because there are 2 very different meanings of that word.
So strongly interacting 3 to 2 in the dark sectors. That's the one.
So what's the initial condition for the SIMP picture? That's this. SIMPs fall into this category. Sure, I was very vague about whether these are 2-to-2 annihilations or something more complicated, but I'm going to throw the SIMP picture, at least as you defined it, in with the thermal freeze-out picture. So you're totally right that the phenomenology is very different. It's interesting and has, in the last few years, been explored in ways that previously hadn't been. But I'm still imagining in that picture something that's in thermal equilibrium and at some point stopped being depleted by its interactions. That's basically what I'm sketching here.
Axion-type things like freeze in.
Oh, so axions and freeze-in I would put as two different categories, okay? So let's do one at a time. So let's do something like misalignment. And here I have in mind something like the QCD axion. Okay, so describe that for the class, or classes as a class, whatever, for the group.
So it's a scalar particle that has a weird thing where when the mass is smaller than the Hubble, as it were, then you have a constant. It's almost kind of quintessence-like. And then once you pass that threshold, it starts oscillating. And so it's just, they're created more or less at rest, and they kind of get a little bit of energy later on, but they're never in thermal equilibrium.
Good. So here you have a particle is never in thermal equilibrium. It starts with a particular field configuration, and as the thermal history evolves, the potential tilts in such a way that there's a new minimum, everything moves to that new minimum, and that motion populates the universe with these particles, axions. So these are not the sort of things that indirect detection people talk about much, but I think it's totally fair to include this on the list of possibilities. It is a well-motivated and viable scenario that doesn't lead to a lot of indirect detection signatures. All right, so you mentioned a second one as well, freeze-in. So just to spread out the interactions, can somebody else tell me what freeze-in is? What do you mean by freeze-in?
You start off with basically no dark matter at the beginning. Then you produce it perturbative laser scattering until you reach sort of a freeze-out temperature, and then you get stuck with it after you've produced whatever you've produced.
Something like that, right? Okay. So you do not start. Not only do you not start in equilibrium, you never reach equilibrium. You have something that has a very, very feeble interaction, and you pick initial conditions, so there's very little of it in the early universe. Didn't have to be that way, but you can select post-inflationary physics to do that. And then it interacts just enough that as time goes on in the early universe, its abundance becomes a little bigger and a little bigger and a little bigger, and never reaches equilibrium, but you get the right amount of stuff to make up the dark matter by the end of the story. Again, not a lot of indirect detection to talk about here, but a perfectly viable scenario and interesting for a lot of reasons. All right, can anyone think of another mechanism, another class of mechanisms? Yeah. Good, yeah, so some out of equilibrium decay. So what I have in mind here is there's some particle that was produced in the early universe, and as the universe expanded, it stopped interacting. It froze out itself, okay? And then because it stopped interacting, it has some sort of matter-like abundance, and eventually that stuff decays, populating the universe with a whole bunch of new particles, which might include the stuff that makes up the dark matter. From a model building perspective, moduli are often talked about in this sort of situation, but it really applies to any generic, very feebly interacting, unstable but metastable particle. Is there anything missing from this list?
It just produced dark matter. Reheating never happened.
Good. Let's think about that. So I would say that is in the out of equilibrium decay example. It's the decay of the impleton that does the reheating in that case. So I would say that is a subset of category 4, but it's a good one, yeah. Yeah, okay. I think it's awfully hard to make all the dark matter be primordial black holes now, but sure, with some caveats. Yeah, I'll put that on there. And one thing that I'm just going to add to this list are freeze-in-like scenarios that are done via oscillations. Okay, so like I have in mind here the Dodelson-Woodrow kind of sterile neutrino picture. So this is not a particle that's scattering to be produced all of this, but it is a particle that as the universe expands and evolves, oscillations populate it gradually, and it was never in thermal equilibrium. So it has a lot in common with the freeze-in scenario, even if it's slightly different.
My eyes suck. Could you write a little bit bigger?
Sure, I will. I promise to do that from here on out. If I don't keep up my promise, scold me, and I'll renew my efforts. All right. So this, I think, is a quasi-complete classification of the ways we've thought of to make the dark matter. I could put the primordial black holes in a list, those 5 things. Well, so I ask you this, like how does an asymmetric dark matter candidate get populated in the early universe? It's really just this picture, except it freezes out a little faster as a result of the depletion of its lesser component, okay? It's still a thermal relic. So I know that asymmetric dark matter is oftentimes talked about like as an entirely different class, but it really isn't. I never specified that this freeze out happens because of Hubble expansion. It could equally well happen because you've depleted all of the anti-dark matter. That works too. Baryons, by the way, are a thermal relic. They're very asymmetric.
What is the distinction between the parenthetical on 3, those oscillations, and the way that the QCD axion field has that oscillation property?
Well, I mean, so in a case of like Dodelson-Woodrow, you're talking about standard model neutrinos oscillating into sterile neutrinos to populate the dark.
Oscillation.
Yes.
Okay.
Yeah. So I'm not talking about. It's a very different thing than the axion-like picture. But yeah, I can see why you were confused though. Okay. So the reason I started with this is because it's a pretty finite list here, and this is probably, arguably, the simplest one to cook up. It appears in a wide class of generic models, and this gives us a clear and interesting, well-motivated benchmark to look for annihilation products. Okay, so that's where we're going to start from. So with that in mind, we're now going to go through the calculation, or at least parts of it, for calculating the thermal relic abundance of a generic stable species, and we're going to find what that teaches us, and then imagine what kinds, or think about what kind of experiments or telescopes we'd want to use to see those annihilation products. All right. So in equilibrium, the co-moving, the number density for a boson or a fermion is just given as follows. How's the size of my writing? Borderline? Okay. So T here is the temperature, so this is just a thermal equilibrium abundance. So if I just take a gas of particles, turn them up to temperature T, this will tell you how many particles will be in that thermal bath of a given type.
So it looks like the dimensionality of those two is different.
That is because there is a typo. That is a 4, thanks. Well, hang on. I've written down, that's in this limit. Yeah, you're totally right. All right, these must be 3s, and I was subconsciously correcting my notes when I must be, right? That's correct. It doesn't bode well for the lectures when the first equation you write down has a...
For n, it's not a 7/8, but a 3/4, and there's a z somewhere. So, well, maybe you can just change it. Those are the correct.
It's possible I just Are these the correct equations for rho, and that was my mistake? Good. All right. Like that? All right. Wow, if there's an error in every calculation, this is going to be some painful lectures. So that's one limit, and I can also write down the other limit. That's backwards. Okay, good. So this is what I'm going to posit. So what I do now?
I think the bottom one is for n.
Is it really? All right. Yeah, of course it is. All right.
I have a conceptual question.
Good.
Why is the equilibrium abundance dependent on the temperature? Surely the equilibrium is an equilibrium.
No. Like, I mean, just think of like black body statistics or something, right? If I take a container, close it, put in a given temperature and let particles bounce off each other, I'm going to generate a number of particles and distribution of those particles that is entirely dependent on the temperature. So if I have, for example, just a small number of particles with a lot of energy in that box, what they're going to do if you let them sit for a while is they'll scatter off each other, make more particles, and spread that energy out over a larger number of particles. So the number of particles or the energy density of particles will depend directly on the temperature of that gas. Does that make sense? Did I answer the right question?
I think so. I think I was thinking of this one.
Okay. So this is the initial condition that we're really talking about, and I'm going to write the following. Okay, and what I've got here is a function of the mass of the particle. No, that's not what I mean. It's a function of x, which is the mass over the temperature. I have the co-moving number density of said particles, okay? By co-moving, I mean that as the universe expands, we're not taking into account that dilution. So a number of particles that is not interacting but is just being diluted by Hubble expansion, that will correspond to a constant value of nx. You can also think of this as the non-co-moving times a cubed. That's a perfectly good way to think about it. If x remains in equilibrium, the number of these particles today will be roughly the number of photons in the cosmic microwave background times this exponent, or e to the minus mass over temperature. This is very small, and therefore you'd be in a situation where you would have an entirely uninteresting quantity of this stuff left. The only exception to that is, I guess, if you make the mass extremely low, but at that point you're left with dark matter that's hot and untenable. So for the sort of range of masses we're going to be talking about here, we can't have a dark matter abundance that is currently in equilibrium. So somehow, as this evolution takes place, the processes that keep something in equilibrium have to cease, leading to a much larger abundance of the stuff surviving to the current epoch. So let's start by saying whatever this particle I'm calling x is, and we're just to call it stable. Okay, we're going to declare it stable by various particle model building means, but I am going to allow processes of the following form to take place, where A just denotes an annihilation product. I'm not specifying what it is, but something like that. And although I'm writing x and x bar as if I'm certain that x has an antiparticle that is not itself, of course this could be a Majorana particle as well, in which case the bar just doesn't mean anything. So if I have something like this, so I have a stable particle, it starts out in equilibrium and it evolves, I can write down the Boltzmann equation to describe its evolution. So the first term, again, n sub x here is that number density. This is just the rate of change of that number density. And I have a term which describes the dilution via Hubble expansion. And here, h is just the time derivative of the scale factor over the scale factor, just the standard thing you derive from the Friedmann equations. And then on the other side, I have the annihilation term. It's not what I meant to write. And that describes the net rate of depletion or production through annihilations.
I think the question goes back over here. When you have n equilibrium,
Yeah.
is that the number density of particles in thermal equilibrium?
Yes.
Or the number density of particles when the species was entirely in thermal equilibrium?
It is the first. So it is the number of particles.
That are still in thermal equilibrium, even when the species as a whole is out of equilibrium?
What I mean when I write down in equilibrium is at a temperature T, the equilibrium distribution will contain that many particles of that species.
Okay.
So what we're going to learn is that the initial conditions start that way and then you're pulled away from that. So in other words, this term does not have to be 0. In equilibrium, this is 0. Okay. So let's think about what that means physically, get some intuition for it. This is 0 when the number density is when it's at equilibrium, simply because in that sort of configuration, for every time two dark matter particles annihilate to produce something else, two something else's annihilate to produce more dark matter. So the production and annihilation are balanced, and that's what maintains the equilibrium. As you move along this curve, of course, the number density changes, but that changes in a smooth way that always guarantees that this goes to 0. And you can see why this is the case early on, because the simple fact that this goes like n squared, and this goes like n. So when n is large, this will be the term that dominates, guaranteeing that you trace that equilibrium curve in the very early universe. I saw a hand up before. That's right. You know what? I misspoke. You're all right. I'm plotting co-moving number density here, and this is just the number density. So in order to make this a little more clear, this means co-moving, and lowercase n from now on, I will use to refer to the actual number density. So you're right. You're right. Okay. So. So let's consider what happens in the low temperature limit. So once the number density in equilibrium gets sufficiently small, okay, so I'm basically doing this where the annihilations have turned off. This has an easy solution. In particular, this will be the solution. The co-moving number density is going to become a constant. This is also what you would intuitively expect when the particles stop annihilating or stop interacting. Their number density become a constant. But let's just confirm that that's in fact the solution. Okay. And I can also, for the second term, and now we just compare these two and find, as we'd expect, that they are equal to each other. So I've just confirmed that, in fact, at some point on the right side of this frame, this goes constant. So what's really important then for our calculation is in determining when this transition from equilibrium to post-freeze out constant co-moving number density sets in. That's going to determine the abundance. Hey, Janet. So I haven't plotted any numbers on this, but this is a log plot in many, many, many orders of magnitude. So if this happened here, or here, or here, you wind up with a very different abundance of this thermal relic. So it's really critical when the freeze out actually sets in. So there are two interesting limits that we can consider. And the first one is historically interesting, but not very relevant for modern dark matter research, but we're going to go through it anyway. It's the example of a hot relic. By hot, what I mean is the value of XF, which is the mass of the relic over the temperature at which it freezes out, is less than maybe a few. Okay? In other words, when it's freezing out, it's still relativistic. In that picture, this is the equilibrium abundance somewhere around, say, here. It freezes out, and its abundance basically stays, its co-moving number density stays approximately at its non-suppressed equilibrium value. The abundance that's produced in this way does not depend strongly on any of the interactions of the relic. Okay, so if I'm talking about, for example, a standard model neutrino, once I know where the freeze out occurs, it's not particularly important what its annihilation cross section is or anything. And that's because you can just simply write down the number density in equilibrium when the thing is hot. And you get something like this, and that just, nowhere in that does depend on the cross section. So the interactions of the particle are not particularly important, except in determining at what temperature the freeze out occurs. Yeah, this error probably propagated. So we'll just do that and hope that's right. Conceptually right. So let's actually do this concretely for the case of a standard model neutrino. So today, I mean, we certainly know neutrinos don't make up a substantial fraction of the dark matter, at least not standard model ones. But this was certainly the leading dark matter candidate for a long time before we knew the things that we know now. So it's a particularly historical, significant is historically significant. And it turns out a generic hot relic has the following abundance. And this is not specific to neutrinos, but it certainly applies. So we have a couple of countings of degrees of freedom here. For a neutrino, the effective numbers of degrees of freedom are just 2 times 3/4. That can't be right. I guess that's right. Maybe there's factor 2 missing there. And then this is for a hot relic is about 10.75. And what I'm talking about here with G star is just a counting of the degrees of freedom available at the thermal bath at the time of freeze out. So we're talking about MEV temperature freeze out, so I add up the numbers of degrees of freedom available in a 10 MeV bath. I count the photons, I count the neutrinos, I count the electrons, and I get this number. This is for one species. Electron neutrinos, mu neutrinos, or tau neutrinos, they're all going to work out to be the same. So if I do this specifically now, putting in the right numbers for neutrinos, I get a number that's about this. And that's 1% of the measured dark matter abundance. 0.1%, I guess. No, 1%. So from this exercise, we've just learned that standard model neutrinos will freeze out in a way that will not significantly contribute to the overall dark matter abundance. This is good because we know from structure formation considerations that the bulk of the dark matter is cold, or at least on the boundary of warm and cold. Certainly not hot. It's certainly not a hot relic that freezes out at a temperature much greater than its mass, as these guys do. Like I said, these guys freeze out at MEV temperatures, and they have masses below an EV. That's a very hot relic, totally unacceptable from a position of structure formation. But all the same, a very small fraction of the overall abundance of dark matter does take this form. All right, so moving on to something more relevant to a modern dark matter perspective, or the generic case of a cold relic. Here I'm going to do the calculation in a limit where the particles freeze out at least on the near side of being non-relativistic. And what this really means in words, I'll just say it, is that the freeze out occurs during this era where the equilibrium number density is rapidly falling. Unlike in the hot case, where you're basically in a flat co-moving number density state when the freeze out occurs. Here we're going to be doing the freeze out while we're falling down this slope. So generically, for any relic that is going to give you about the right abundance, any cold relic that gives you about the right abundance, this freeze out will occur at a value of x of 20 or 30. Now this is a numerical fact. I thought about trying to do that on a chalkboard, but frankly, I only believe this is true because when I write a Boltzmann code and run it on my laptop, it gives me that answer. I don't really have an intuition for why it's not 3 or 45 or something. But what that basically means is that you're in a situation here where you're well down this curve by the time the annihilations become inefficient and you freeze out of thermal equilibrium. Let's say, for example, that this is about where the temperature is approaching the mass. We're talking about something a factor of 20 or so to the right of that. So you're well down this curve. So now, for this generic cold relic, we can calculate the abundance that survives. And it turns out, I'll write down one step here before giving you some numbers. And so it linearly depends on the x value at freeze out. Implank comes in from the dependence on the Hubble parameter, Hubble expansion rate. G star is the same counting of degrees of freedom we talked about there, and it depends on the temperature freeze out. And then this with the brackets around it is the annihilation cross section times the velocity relative velocity between two WIMPs. The brackets are the thermal averaging. And I will say that it's common to write this as an expansion in powers and even powers of velocity. Okay? This is usually a convenient and safe thing to do. There are exceptions, and we'll talk about some of them later. But actually, I did this wrong. There shouldn't be brackets here. And then the thermal average of this is going to look like A plus 3B over X freeze out. So that's what the thermal average gives you. And then one last step. This abundance becomes the correct or the desirable number to give you the full abundance of dark matter for a wide range of masses for an annihilation cross-section thermally averaged, which is about 2 times 10 to the minus 26 cubic centimeters per second. Just for record, this is the measured value of cold dark matter. So I scaled this to 0.11 in order to get the right amount. So if the dark matter, and by the way, if you want to change this result, you have to do a few very specific things. You need to change early universe cosmology, make it not be ordinary radiation-dominated expansion. Or you need to go very heavy or very light, in which case this quantity, and to a lesser extent this quantity, will change a little bit, moving this cross-section slightly up or slightly down. But basically, for a wide range of cosmological scenarios and masses, this is about the right answer. At the level that I'm trying to present things here, you can treat it as the right answer. So if there existed a particle and it interacted a lot more than this, okay, it annihilated very, very efficiently. You would put in a large number here. This would be small, and therefore the abundance you would wind up with would be well below the measured dark matter abundance. And turning it around the other way, if you had a particle that was very feebly interacting, but interacting strongly enough to have started in equilibrium, that particle will freeze out earlier and give you way too much dark matter. That's ruled out by the virtue of the fact that there's only the measured amount of dark matter in our universe. So we're used to putting limits on dark matter which say their interactions can't be stronger than a certain amount. The relic abundance considerations gives us a way of limiting from the other side, saying that anything that interacted less than this amount would have been overproduced in the early universe in a way that would be unacceptable, without changing things like early universe cosmology, or introducing a new mechanism to deplete it. Any questions? Yeah, and Beck. I'm sorry, could you repeat that? I couldn't quite hear you.
It figures the value of x at which the value of nx starts dropping. How do we get that value to be 3?
So you mean when I wrote down this? Okay, so that's an imprecise number. I'm just saying that you're on either on the very relativistic side of things or very non-relativistic. You can of course consider a case where you're near, you're freezing out when things are a little warm. That's perfectly acceptable as well, and you'll get an answer between the two. So I just considered two limits. But there's no reason the Boltzmann equation could not be solved for something in that intermediate regime as well, for a warm relic, if you will. Yes?
Even though it's thermally averaged, the cross-section into brackets, I feel like that still depends, it's averaged across all the temperatures of the particles that you have at that time.
All the velocities, it's one temperature.
But the temperature, the distribution of those velocities is going to depend on the temperature overall. So it's going to be change as the universe evolves.
No.
It's time dependent in that region.
Good. So this is the cross-section at a temperature of freeze-out. Okay. So you're right. This has a temperature dependence to it. Agreed. This is the thermal averaging at XF, which means at TF equals MX over XF. Good. And like later in the universe where we're going to be interested in the velocities become small in most environments, and these terms essentially go away and the cross-section just reduces to A, thermal average or otherwise. Other questions? Okay. So let's take this argument then, this sort of classic generic thermal relic, and try to figure out what we can say about, for example, its acceptable range of masses. Is there any reason I couldn't consider a thermal relic as dark matter that's arbitrarily light? As long as it froze out in a cold way?
If it's arbitrarily light, it froze out in a cold way. That means when you freeze out much later. The wind was cold, maybe it freeze out to afterwards. For me, that's a problem.
When I say something's cold, what I mean is when it froze out, it was non-relativistic. That's if I'm being precise, that's what I mean. And you're right, it would be some weird cosmology. But it turns out well before we get to anything that weird, we hit a different boundary. Can anyone think of a constraint that so for example, let's be concrete. Can I write down a 1 MeV cold thermal relic? Is that an acceptable hypothesis at this time? Why not? Small scale structure, okay. Well, no, I mean, if it's cold enough, it wouldn't.
I mean, if it's coupled with standard model, probably you're annihilating into standard model radiation stuff, and that would mess up BBN.
Good, BBN, okay. So the BBN is going on at temperatures around an MeV. An MeV relic will be freezing out at about 1/10 of an MeV, okay? And at 1/10 of an MeV, if you're dumping an equilibrium number density of stuff, energy, into the universe, you will radically destroy those successful predictions for the light element abundances. Okay, but let's say I, for example, annihilate entirely the neutrinos. So neutrinos aren't breaking up any nuclei. Do I have anything to worry about there? Or maybe I'm annihilating into a hidden sector that, again, doesn't break up any nuclei.
It changes ineffective if you delete neutrinos or anything else.
Good. So I'm going to rephrase what you said, but you're entirely correct. If you're annihilating even to neutrinos at a time during or after a BBN, you are introducing more energy and radiation and light particles during this time, which changes the expansion history, and you can't change expansion history a lot during BBN. You can a little bit, but not very much. So we have a constraint. It turns out to be around 10 MeV. Anything below that is going to lead to considerable problems. Yeah?
What happens after BBN, right? So I have BBN told me what's going on. It's 1 MeV, 10 MeV.
Okay. Well, BBN tells us not only what was going on at BBN, but it tells us a lot about the expansion rate ever since. Okay, so if you deposit a lot of energy and radiation at any point after BBN, you will change this quantity ineffective or delta ineffective if you prefer. So you can't just make it happen later. That won't evade the problem. You also run into problems with the CMB. We measure the CMB very well, and even small departures are the sort of things you can maybe notice there. And we'll talk about that later. So, of course, there are a lot of dark matter candidates lighter than 10 MeV that are talked about. Why do those evade the constraints I'm talking about here? What's a main assumption I'm making that allows me to make such sweeping statements?
Thermally connected to the standard model with a pretty big element. So like you could use like an elder or something and elastically decouple.
For the sake of the room, just define the word elder.
Yeah. So there's this cute scenario where you elastically decouple before you freeze out your number density, and then you wouldn't have you wouldn't necessarily have a problem.
Okay. I'm going to say what I think you're saying in attempting to do it in a more sweeping way. If I go to these 4 or 5 categories we started with, anything that starts in thermal equilibrium, I think you can make this 10 MeV statement about. If you started with that sort of abundance, that full thermal equilibrium abundance, and you let that annihilate substantially at a time after about an MeV, you are going to ruin everything we know about the universe, or a lot of what we know about the universe. So axions, for example, don't have this problem. There were never that many axions. There was never a big energy density of axions in the early universe. It was produced later by misalignment. You can do that arbitrarily light. I can take a light hidden photon and have it freeze in. Or I can take a light sterile neutrino and have it oscillate in through Dodelson-Woodrow. None of these scenarios involved a particle that started out in thermal equilibrium, and therefore none of these limits apply, and none of these constraints apply. But for the one that I have the box around, I think it's very hard to imagine a scenario that you could go much lighter than this. Yes, Tracy. Yeah. So he has a cancellation, right? So he screws up ineffective in one way and then screws it up in the opposite way. Yes. And Asher's brilliant. He outsmarted the limit. But I think if he were here, I could convince him that it's fair to call that tuned and move on. I think the world of Asher, his paper is entirely correct, and it does seem to violate this, but it involves a cancellation of 2 terms. Good point. I'll have to cite that in my TOSI lectures as a caveat. All right, let's go to the other direction. This is the lower mass that we could consider a thermal relic dark matter candidate. Can I go to arbitrarily high masses? Okay. Care to elaborate?
Sure.
Expand on that. You're entirely correct, but expand on it. Okay. Explain where that comes from.
So if you assume a certain cross-section, particularly an S-wave cross-section, then you can derive unitarity bounds coming from the lowest of the and using this freeze-out relic, you arrive at about 100 TeV.
Good. So I'm going to put what you just said in different words, but I entirely agree with your conclusions. If you had a particle that starts on a thermal equilibrium with a mass higher than about 100, 120 TeV, something like this, quantum field theory alone just simply says it can't annihilate enough to be depleted to an acceptable level. You will have too much of this stuff, invariably, independent of the particle physics details, if the mass exceeds, I think it's 120 TeV. Carlos, am I, okay, all right.
Could I ask how does this work? Is it sigma b equals alpha square over m, and then or m squared, and you scale alpha and m?
So you can do it in a very model-independent way. So this 1991 or 2 paper by Kamiankowski and Greece do this without taking on any details of the particle physics. They're just going to say whatever the amplitude is, we're going to expand it in partial waves. We're going to take this one term and we're going to saturate it, and this is the limit. Now, you can get stronger limits than this, writing down a specific form of the amplitude. But this is going to be the weakest limit, independent of the underlying particle physics in your theory. Tillman. No, they have a whole section in that paper on composite scenarios, and it doesn't, in the large form, change the answer. But they did worry about that. I saw another hand somewhere. Yes.
So there's an amplitude, I'm not sure if it's the same one. The idea was that if they're too massive, that there's not that many of them, and so it turns out they don't hit each other enough. They can't find a partner to annihilate with often enough, so they wind up freezing out earlier than you wanted them to, just because they can't annihilate as much, or
Sure.
it doesn't work that well.
Good. So I think what you're saying is entirely cogent with this. I would say that you might have guessed, if you didn't know QFT, that you could just turn up the cross-section arbitrarily high to balance that, to overcome the fact that the number densities are lower. But the unitarity bounds on amplitudes in QFT tell you there's a limit to that, and that's where the limit forces you to. So I think you're thinking about it from a different perspective, but it's really the same thing underpinning it.
I got to ask this dumb question. You said that was for the S wave. Why do we know that the other waves can't contribute enough to get the cross sections high enough?
Yeah. So I think we're in danger of getting a little technical, but I believe the Kamienowski and Griest argument is presented in a way that's independent of which waves dominate. You do it one at a time. You ensure that yeah. But Carlos, I think you know more about this than I do.
Higher partial waves is balanced by an order of 2 to 4. It's really hard to get past that. But really the only way around it is to make a resonance through
And it has to be a narrow resonance, right?
Well, in other cases, so in principle, you might have a very light mediator, like a very massive, because in general, the higher partial waves get suppressed to low velocity. It's basically because they correspond to collisions with the higher path. But if I have a very much interaction, then the higher partial waves don't get suppressed. Like roughly scattering. So I know there are if you say, okay, I don't care about the constraint stuff at a interaction, like that's a situation where you're having I mean, it's sort of similar to resonance, but I mean, you're some very tiny scale. So in that case, I think you may be able to get
In the window, when you're still okay with BBN, I think it's only like a factor of 4.
okay.
Yes.
For context, do you know off the top of your head the velocities and temperatures whatever GeV?
Yeah. So where freeze out is occurring, okay, so when X, that's what matters, is what X freeze out is. For 20 or 30, V squared is about 0.1 in units of speed of light. Okay, so what we've just learned from these exercises are somewhere that we can motivate our searches for. This mass range, approximately, is I think where one would look for an annihilation signal. And this cross-section gives us an idea of what we should naively expect the overall flux to be set by. Okay. Now, later in these lectures this week, we're going to show, or I'm going to explore a lot of the exceptions and caveats to this. You can find a lot of models where the cross-section is not 2 × 10⁻26. In fact, I'd say the average WIMP paper written has a cross-section that isn't that number. But they usually fall within an order of magnitude of that, not always, but usually. And we'll talk about the various ways that plays out. But I think it's fair to say that if you want to test a substantial fraction of WIMP models, you would like to be able to, across this mass range, test cross-sections that are about that big. And if you could go even lower, you can test even more. But if you could do that, if you could accomplish that, you could test a lot of the things that we would call a thermal relic dark matter candidate. So setting up for next time, I've got 15 minutes left, I think. Let's kind of just talk about what the signals are that we might be looking for, and then next time we'll actually talk about what those signals might look like in some detail. The first and by far most studied option for indirect detection are just looking for high energy photons that come from dark matter annihilations. This has the longest history as well. So in 1978, 2 papers, both in PRL, were published on the same day. It was on Valentine's Day of 1978. I like to joke that this doomed a bunch of hopeless romantics to looking for dark matter in the gamma ray sky for decades to come. One was Jim Gunn et al., and that includes Ben Lee, David Schramm, Gary Steigman, some others. And then there was also a Floyd Stecker paper, and both of these were in this, the February 14, 1978 PRL edition. And there were a lot of things in 1978 that they didn't know that made some of their calculations not super relevant to modern searches. In particular, they really, the WIMP paradigm hadn't come into fashion yet. They were talking about a heavy stable lepton, which of course could have been a standard model neutrino, but they had something more generic in mind. So they had in mind that there was something like a neutrino, maybe a neutrino, that was stable and was GeVs in mass. So that's what they sort of had in mind. We didn't know much about how dark matter was distributed in the universe or in the Milky Way. We only had the slightest clues about structure formation and galactic rotation curves and things like this. So they didn't know exactly how to calculate what the annihilation rate would be in the galaxy or elsewhere. But they did realize something important. If you just did a naive calculation saying, we know how much dark matter there is in the universe roughly, if it were smoothly distributed, you'd get one annihilation rate, and that would be undetectable with the technologies at the time. But they correctly pointed out that this could be true. The average of the density squared of dark matter could be much higher than the average of the average density quantity squared. And those inhomogeneities in the dark matter distribution can boost the overall annihilation rate in the universe by large factors, making these sorts of signals potentially observable. And we'll talk about that in detail, but even in 1978, that was appreciated by both groups. Also at the time, the experiments were nowhere near as sensitive as they are today. They had something called the SAS that had made a measurement of the diffuse gamma ray background, but this was in an energy range of tens of MeV, not exactly the first place you'd want to look for dark matter annihilation products. And they didn't have much spatial information, they didn't have much resolution. Years later, other experiments like something called COAST-B, followed by Egret and now Fermi, have improved on this dramatically. And we've gone to beyond the GeV range with ground-based telescopes like Hess, Veritas, MAGIC, and HAWK, and they give complementary information for heavier WIMPs that these space-based experiments can't do. So, moving to the future, in 1984, people started talking about antimatter annihilation products as a signature of annihilating dark matter in the halo of the Milky Way. The first paper on that was by Joe Silk and Srinecki. And then in 1985, just a year later, Lawrence Krauss, Katie Fries, David Spergel, and Press, as the Press Schecter guy, we're talking about neutrinos, in particular within the context of neutrinos produced in dark matter annihilations in the core of something like the sun. And that more or less set the stage for the next few decades in indirect detection. Kind of like the 1978 gamma ray papers, the authors of these papers didn't know many of the things we know now. Okay, they knew more than they knew in 1978, but we didn't know much about cosmic ray propagation or production or things like this. We still didn't know that much about how the dark matter was distributed and things like this. But the estimates that were put forth in these papers are, very roughly speaking, similar to the sort of estimates we would make today. We have many more details and bells and whistles included, but the idea is to go back at least that far. So I could extend this a little bit too. In terms of experiments, there were a lot of cosmic ray experiments in between, but this really heated up. Oh, excuse the pun, that's a terrible pun. With two flights of something called the HEAT experiment, which measured the first hints of a positron excess in the cosmic ray spectrum. That was in the late 90s and early 2000s. And then that was confirmed later by the Pamela satellite, which measured that positron excess in much higher detail. And then more recently with the AMS experiment on the International Space Station. And then antiprotons were also scrutinized by a number of different experiments along the way, including Pamela and AMS. We'll talk about that in more detail later. In terms of the neutrino channel, there have been a lot of experiments along the way that have contributed. These include things like Kamiokande, large volume experiments like Amanda and Antares, and now IceCube, and they all provide complementary information. So gamma rays aren't the only kind of photon we'll talk about too. We'll talk about signals in the X-ray band and even radio band and things like this, depending on how much time we have left. All right, so that's setting the stage. I'm about to start on the gamma ray section, but if there are any questions, this would be a good time for them. All right, so we'll just start on the gamma ray discussion, knowing that we're going to have to pick up where we leave off tomorrow morning. Okay. So let's just make a couple of very generic statements first. The annihilation rate of dark matter per volume, I can write as follows. I think a lot of those terms will be pretty self-evident, but can anyone explain the factor of 1/2? Why that's there? That's probably the least obvious piece of this expression. I am assuming that it's Myron, or more specifically, that it's its own antiparticle. Yes. Explain what you mean, but yes.
You're trying to see how particle 1 looks like the particle 1 meeting particle 2, but you don't want to double count it as 2.
Good. So if I didn't have the 1/2, what I'd be calculating was how many times particle A annihilated with B, and separately counting B with A, and therefore getting a factor of 2 too high. So that's just a double counting issue, just like Carlos said. So from this, I can calculate the flux of some annihilation products. In this case, we'll talk about gamma rays. You're discontent with something about my lecture, Tillman?
I am, for the first time in my life, I'm seeing your variable to factor 1/2, and I think that's great.
It doesn't happen very often, it's true. All right. All right, so this is the flux as a function of energy and what I'm calling delta omega, which is just some piece of solid angle. Okay, so we're going to integrate over some piece of solid angle that we're going to point our telescope in. And I'm going to put this very important factor of 1/2 out front. It's supposed to be funny. And I'll explain these pieces in a moment. Okay. All right, so this thing here is the spectrum of annihilation products per annihilation. Yes? So could you repeat that?
Should that be d5
d phi dE.
Your underground, I think she
It's
means.
not the flux, it's
Is this thing? Yeah, so that's how I'm defining this. This is the spectrum of annihilation products you see in some cone delta phi. Yes, to be clear, this has 1 over energy units.
Where's the line of sight?
Let me go left to right. Okay, so this thing here is the spectrum of the annihilation products in question and gamma rays per annihilation. Okay, so if I have 2 particles annihilating, that is the spectrum of gamma rays they will get produced on average. This integral is over that angular solid angle cone that you're observing, whatever you call it. And then LOS here stands for line of sight. Okay, so L is the line of sight being observed. So here is some solid angle, and I'm going to integrate throughout this solid angle along a line L that I'm observing. And then rho is just, I should put the X on it. This is the dark matter density squared along that line of sight, which depends, of course, on the angle that you're pointing in and the length along that line of sight.
So the radial distance to which you're integrating depends on how far it goes before you hit something in that angle? Is that
This integral or this one?
the line of sight one, where you're integrating out?
To infinity.
Okay.
Okay, I'm not treating any absorption in this problem. I guess I'm assuming 2 things. The photons aren't being absorbed, and we're talking about emission well within redshift of 1, so like nothing's getting redshifted substantially. If you want to calculate the diffuse background from annihilations throughout the entire observable universe, those things both are not true, and we need to include that. So this is, I have in mind maybe things in the Milky Way or even clusters this would be appropriate for. All right, other questions? All right. So let's try to build up some intuition by considering some like toy examples. So I'm going to consider a region with a certain abundance of dark matter in that region. Has a volume V, so the abundance is, or the density is flat within that volume. And I'm going to say it's a distance d away, which is large compared to the size of that volume, linear size of that volume. So this whole thing is oftentimes referred to as the J factor. And I don't know where the word J came from. I think probably just the 1994 Bergstrom-Buckley paper called it that, and it's stuck. But we still call it the J factor, and it encapsulates all of the information about astrophysics that we care about. It tells you where the dark matter is and how it's distributed, how far away from us it is. All that stuff is encoded in the J factor. So our J factor in this case is really easy to calculate. It's not always, but it will be.
I can't see, is that a D much greater than?
Yeah, so this is the distance to the region in question. So here's what I have in mind. I have a region, a volume V with a density, and I'm here. This is the distance to it, and I'm going to calculate the flux of gamma ray products from dark matter annihilating in that region. If you want something more concrete, think of it as a dwarf galaxy. Okay, so I write down the expression for the J factor, and it turns out in this extremely simplified case I get the following. And that means my annihilation products will have the following flux and we can use this to get some intuition for where we might want to point that gamma ray telescope we're relying on. What kind of targets are the most favorable from this perspective in terms of looking for annihilation products? Sorry? Okay. So nearby, small d, dense, high rho, and I can think of at least a third thing which the equation doesn't encapsulate, but we should probably consider. If I have two objects at the same distance with the same dark matter density, are they always going to be equally attractive targets? Low background. Okay, so next time we're going to start with this. We're going to list a bunch of different targets for gamma ray searches for dark matter, and we're going to consider ones that maximize the combination of these three factors. Some of these are going to be really faint signals with really low background that are clean, and some of them are going to be ones really huge signals, but frankly hard to separate from the astrophysical backgrounds, and then things in between. And then we're going to do some calculations and look at what the limits are, see what we can learn from experiments like Fermi and others. I think gamma rays will probably be most of Tuesday's lecture, if not all. Any closing questions before we break? Yes? Sorry, say again? Yeah, that will be a big part of tomorrow's lecture. Yeah, that's a long story. Short answer is angular and energy information, spectral information, and how it's distributed in angle. Those are the only tools we have. All right, well, yes?
Possible dark matter candidates. You told about standard model neutrinos, but then it was ruled out because of that small relic density.
That, and also they would be hot. And we know from structure formation considerations that dark matter can't be hot. When we compare the distribution of galaxies and other sorts of things in the universe to numerical simulations, it tells us very clearly that whatever dark matter is, it must have been cold or at most warm at the time of decoupling.
But what about sterile?
So sterile neutrinos are produced in a different fashion. The sterile neutrinos that people consider as dark matter candidates are not the sort of thermal relics we're talking about now. They're produced by maybe various mechanisms, but Dodelson-Woodrow is a classic one where they oscillate into their current abundance. It's reminiscent of, but not identical to Friesen. So that doesn't apply to these calculations. That's a different sort of dark matter candidate.
I don't really see so the integral there for the why
Good. So this just goes out front, right? Okay. And then you end up, let's see. This is going to be the volume of that sphere divided by 1 over 4 pi d squared. Right. Right. So that's where the d squared comes from. And intuitively, it has to be true, right? I mean, this is the reason why, long-range forces have 1 over d squared in their forces, right? I mean, fluxes by geometry alone have to decrease like 1 over d squared.
Yeah, just like maybe another way to say that is that getting like rho squared over r squared times like rho squared over l squared times l squared. Yeah. I don't know
Oh, sure.
if, it's just the major involved in that, then you have 1 over l squared, which is approximately 1 over d squared.
Yeah, I like that. That's good. All right. Thanks, everyone.